Imagine an explosion, not of fire, not of sound, but of pure reality itself. A moment when everything, space, time, energy, erupted from absolute nothingness. No stars, no galaxies, no atoms, not even the fundamental forces of nature. Just an unfathomable singularity, teetering on the edge of existence. And then, it happened. The Big Bang. But what came next? What happened in the first second after the universe was born? This is a story of chaos, transformation, and the birth of everything we know. To truly grasp what unfolded in this minuscule sliver of time, we need to redefine our sense of scale. A single second in our daily lives feels instantaneous, barely a blink. But the first second of the universe? It was an epoch, a vast sprawling drama playing out in unimaginably small fractions of time. Scientists divide this second into distinct eras, each lasting mere microseconds or less, yet shaping the cosmos forever. And it all starts with a moment so short it defies human intuition: the Planck era. The Planck era existed within the first. 10 to the power of -43 seconds, a duration so brief that it is the smallest unit of time in physics, called the Planck time. At this scale, the universe wasn't just tiny. It was a singularity where everything, matter, energy, even the fabric of space and time, was compressed into an unfathomably dense point. Temperatures soared beyond 100 million trillion degrees, a state so extreme that conventional physics simply breaks down. The universe was smaller than a proton, yet contained all the energy that would ever exist. In this bizarre state, the four fundamental forces of nature, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, did not exist separately. Instead, they were fused into a single unified force. This means that the laws of physics as we know them hadn't even been written yet. Gravity, which today governs the movements of planets and stars, was indistinguishable from the forces that hold atoms together. Imagine a world where the very concept of attraction, motion, or even cause and effect were uncertain, where the rules of reality itself hadn't yet formed. But the universe didn't stay in this state for long. As it expanded, something crucial happened. Gravity broke away from the unified force. This wasn't just a minor separation, it was a fundamental shift in the way the cosmos would evolve. The universe was beginning to establish the framework that would govern everything from the movement of galaxies to the bending of space-time around black holes. Now, we move to the grand unification era, occurring at around 10 to the power of -35 seconds after the Big Bang. In human terms, this might seem like an imperceptible instant, but in the language of the cosmos, it was an era of incredible transformation. The universe was still unfathomably hot and dense, but it was now expanding rapidly. The strong nuclear force, the force that would one day bind atomic nuclei together, was on the verge of separating from the unified force. This seemingly small event had colossal consequences, and then something unimaginable occurred: inflation. This wasn't just an expansion, it was a radical exponential eruption of space itself. In less than a trillionth of a second, the universe expanded by a factor of 1 followed by 26 zeros. To put this into perspective, if a single atom had undergone the same rate of expansion, it would have swelled to a size larger than our observable universe today. Space-time itself stretched and expanded at a speed far exceeding that of light, not violating relativity, but rather carrying everything with it in an unstoppable surge. What caused this sudden burst of inflation? Scientists believe that the fabric of space contained a form of energy, sometimes referred to as the inflaton field. At a critical moment, this field underwent a phase transition, releasing an enormous amount of energy and triggering inflation. But the consequences of this were even more profound than mere expansion. Inflation smoothed out the universe, erasing any pre-existing irregularities and stretching quantum fluctuations, microscopic distortions in space, across vast cosmic scales. These tiny variations, magnified across billions of light-years, would later determine the structure of the entire universe, where galaxies would form, where vast voids of empty space would exist. The very architecture of the cosmos was etched in this instant. Then, just as suddenly as it began, inflation stopped. The universe's rapid growth slowed, but the immense energy that had driven inflation didn't simply vanish. Instead, it transformed into a searing bath of particles and radiation, giving birth to the first fundamental components of matter. This marked the start of the electroweak era at around 10 to the power of -12 seconds after the Big Bang. At this point, the universe was still blindingly hot, exceeding 100 trillion degrees, but something remarkable was happening. Particles were forming. For the first time, the universe wasn't just a formless sea of energy. It had begun the process of creating the building blocks of all future matter. But there was a problem. As quickly as particles formed, they collided with their opposites, antiparticles, and annihilated each other in bursts of pure energy. Imagine a cosmic battlefield where creation and destruction waged war in perfect symmetry. Every particle had a counterpart. An electron had a positron, a quark had an antiquark. Whenever they met, they obliterated each other. If this perfect balance had continued, the universe would have remained a void, empty, lifeless. Nothing but light, but something tipped the scales. A minuscule asymmetry, about one extra particle for every billion particle-antiparticle pairs, meant that matter had a slight advantage over antimatter. It was the tiniest flaw, an imperfection so small it almost seems trivial. But without it, none of us would be here. That tiny excess of matter is what survived, what went on to form stars, planets, and everything we see today. If the universe had been perfectly symmetrical, all the matter and antimatter would have annihilated each other completely, leaving behind nothing but radiation. This delicate imbalance, this cosmic fluke, determined the fate of everything. Every atom in your body, every drop of water, every grain of sand exists because of this 1 in a billion imperfection in the early universe. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free and it helps us grow this community together. By this point, we're still not even at a full second after the Big Bang. Forces had split, inflation had carved out the vast expanse of space, and matter had barely triumphed over annihilation. But the battle wasn't over yet. The universe was still a violent churning inferno, filled with high-energy particles colliding at unimaginable speeds. So what happens next? How do these chaotic high-energy particles evolve into the first recognizable atoms? And what other surprises lurked in the earliest moments of the cosmos? The story of the first second isn't finished yet. At this point, we are still within the first second after the Big Bang. The universe is a roiling cauldron of energy, a violent sea of searing hot plasma where the rules of physics are only just beginning to emerge. It is expanding rapidly, cooling fraction by fraction, but still unfathomably hot, billions of degrees in every direction. And within this cosmic inferno, something crucial is about to happen: the formation of the first real building blocks of matter. We left off in the electroweak era, where the electromagnetic and weak nuclear forces remained unified, and where a cosmic struggle between matter and antimatter had already been decided by the tiniest, most imperceptible imbalance. But this battle was not without consequences. The universe was now filled with an intense, high-energy soup of quarks, gluons, leptons, and radiation. There were no atoms yet, no protons or neutrons, no stable structures. Everything was free-floating, colliding at speeds near the speed of light, annihilating and reforming in an endless, chaotic frenzy. And then, as the universe continued to expand, something extraordinary happened. At around 10 to the power of -6 seconds after the Big Bang, just a millionth of a second, one of the most critical transformations in history took place. Quark confinement. Up until this moment, quarks, the fundamental building blocks of matter, existed freely, swirling chaotically in the plasma like tiny energetic fireflies. But they couldn't stay that way forever. As the temperature dropped just enough, quarks found themselves drawn together by the strong nuclear force, forming larger, more stable entities. This was the birth of hadrons, the family of particles that includes protons and neutrons, the very same particles that would one day form the atoms of everything in existence. But why did quarks suddenly decide to bind together? The answer lies in the nature of the strong nuclear force, one of the most mysterious and powerful forces in the universe. Unlike gravity, which weakens with distance, the strong force behaves in a bizarre way. The farther quarks try to separate, the stronger the force pulling them back together. It's as if they are bound by an invisible, unbreakable elastic band. At this critical moment, as the universe expanded and cooled past a certain threshold, quarks could no longer resist this pull. They locked together in groups of 3, forming the very first protons and neutrons. This was a turning point. For the first time, stable structures, however primitive, existed in the universe. The raw chaos of the early plasma had given way to something recognizable, something enduring. The foundations of atoms, and by extension, all of chemistry had been laid. But the universe was not yet at peace. In the next fleeting fractions of a second, a new catastrophe loomed on the horizon, the annihilation of the hadrons. As soon as protons and neutrons formed, their evil twins, antiprotons and antineutrons, also emerged. And just like the earlier battle between matter and antimatter, these opposing particles met in violent collisions, annihilating each other in explosions of pure energy. The universe became a battleground once more, with protons and neutrons struggling to survive against their own antimatter counterparts. But just as before, that tiny, 1 in a billion imbalance, the slight excess of matter over antimatter, saved the day. While most of the hadrons annihilated each other, a small fraction remained. These surviving protons and neutrons would go on to form the atomic nuclei of every element in the cosmos, from the hydrogen in distant stars to the carbon in our bodies. Now, at around 1 microsecond after the Big Bang, the universe had transformed once again. No longer just a chaotic plasma, it had now become a sea of stable hadrons, protons and neutrons, swimming through a still searing ocean of high-energy radiation. The fundamental forces were nearly in their final form, and the stage was set for the next great leap, the formation of atomic nuclei. But the universe was still too hot. If protons and neutrons tried to combine, they would immediately be torn apart by the sheer energy of their surroundings. For now, they remained independent, waiting for the moment when temperatures would drop just enough for them to fuse into something greater. That moment was still seconds away, an eternity in the timeline of the cosmos. Yet in this same tiny window of time, another event occurred, one that would shape the very nature of reality itself, the separation of the electromagnetic and weak nuclear forces. Up until now, these two forces had been intertwined, acting as a single unified force known as the electro-weak force. But as the universe continued cooling, another dramatic transformation occurred, one that had profound consequences for the physics of the cosmos. The weak nuclear force, responsible for radioactive decay, and the fundamental interactions that would later govern nuclear fusion, split away from electromagnetism, creating the force structure of the universe as we know it today. This separation wasn't just a theoretical shift, it physically changed the way particles interacted. It determined how atoms would form, how stars would shine, and even how life itself would one day exist. The physics of our world had taken its final shape, locked in place by the conditions of this fleeting moment. And yet we are still not at the 1 second mark. The universe is still incredibly dense, unimaginably hot, and teeming with high-energy radiation. But the pieces are now in place. Protons and neutrons have formed, surviving their battle against annihilation. The 4 fundamental forces, gravity, electromagnetism, the strong nuclear force and the weak nuclear force, are now fully distinct, governing the interactions of everything to come. And the universe continues to expand, cooling ever so slightly with each passing instant. But what happens next? If protons and neutrons have formed, when do they begin assembling into actual atoms? And what role does radiation, still flooding the cosmos, play in shaping the early universe? Now we are approaching a critical moment in the universe's journey. just a fraction of a second away from what would be the first real building blocks of the cosmos. We've seen protons and neutrons survive their annihilation with antimatter. The forces of nature have split, and the universe is expanding. Still an incredibly hot, dense, and chaotic soup. Yet, despite all this, we have yet to see the true formation of matter as we understand it. The universe is on the brink of something monumental. The first atoms are about to form. This critical moment occurs when the universe is just under 1 second old. But before atoms can take shape, another process must unfold. The temperature must drop enough to allow the protons and neutrons, those foundational particles of matter, to stick together, forming the very first atomic nuclei. This process, known as nucleosynthesis, began when the universe cooled enough to allow protons and neutrons to overcome the intense thermal energy and begin binding together. By 3 minutes after the Big Bang, the temperature of the universe had dropped to around 1 billion degrees Celsius, a temperature still incredibly hot, but cool enough for nucleosynthesis to proceed. At this stage, protons, which are positively charged, and neutrons, which are neutral, began combining to form the first light nuclei, mainly hydrogen and helium, along with trace amounts of lithium and beryllium. Imagine the universe at this moment as a vast cosmic furnace where nuclei are being forged in rapid succession. The universe is still a swirling hot soup of plasma, but now the building blocks of everything, every star, every planet, every living thing, are beginning to emerge. The nuclei formed in these early moments would eventually combine with electrons, which were still floating around, to form the first atoms, but not just yet. The universe was still too hot for stable atoms to exist. For now, what we have are atomic nuclei, floating in a sea of free electrons and high-energy radiation. Now you might be wondering, why didn't these nuclei instantly form stable atoms? Why didn't we have hydrogen gas right away? The answer lies in the interaction between photons, light particles, and electrons. The universe, still extremely hot, was bathed in intense radiation. Photons bombarded free electrons, ripping them away from atomic nuclei and preventing the atoms from forming in the first place. The process known as recombination, when electrons would finally latch onto nuclei to form atoms, was still some time away. But we are on the verge of it. The universe was nearing a temperature where this process would become possible. At this stage, the universe had reached a crucial turning point. It was cooling and evolving from a dense, chaotic plasma into something far more structured, far more recognizable. While the first stable atoms wouldn't form for another 380,000 years, the groundwork for all of matter was being laid right here. The raw ingredients for stars, galaxies, and planets were slowly, almost imperceptibly, coming into existence. The story of the universe was unfolding, not in grand cosmic explosions or fiery collisions, but in the quiet, subtle bonding of particles. As nucleosynthesis continued, the universe was also taking its first steps toward the formation of cosmic structures, the vast clusters and superclusters of galaxies that would eventually form the cosmic web. While this process took millions of years, the seeds of these structures were sown in the fluctuations created by inflation during the very first moments of the universe. Tiny differences in density, stretched across unimaginable distances, would gradually give rise to the gravity wells that would pull matter together, forming the galaxies and stars that we observe today. But what's truly remarkable about this period is the universe's rate of expansion. Although the universe was still incredibly young, it was already beginning to show signs of a delicate balance. If the universe had expanded too quickly, it would have cooled too fast for nucleosynthesis to occur, and we would have had a universe of hydrogen gas with no heavier elements to form stars or planets. On the other hand, if the expansion had been too slow, gravity would have caused matter to collapse in on itself, possibly leading to a big crunch that would have destroyed everything before it could fully evolve. This incredibly delicate balance between cooling, expansion, and gravity is what allowed the universe to evolve into the place we now inhabit. It was also during this time that light, or more specifically photons, began to interact in a new way. For the first time in the universe's history, things were starting to cool down enough that photons were no longer constantly scattered by free electrons. This marks the birth of the cosmic microwave background, CMB radiation, which is essentially the first light emitted by the universe. This light is still detectable today, billions of years later, and provides us with a snapshot of the universe when it was just 380,000 years old. This light, this glow, is the oldest radiation we can still observe, and it carries the story of the universe's earliest moments. But the formation of the CMB was not an immediate process. At this point, the universe was still bathed in a fog of plasma, and photons were constantly scattering off free electrons. This photon bubble would persist until around 380,000 years after the Big Bang, when the universe finally cooled enough for electrons to combine with protons and form neutral hydrogen atoms. This event, called recombination, would lead to the decoupling of light from matter, allowing photons to travel freely through space for the first time. So what does this all mean for us here today? The first second of the universe was the start of everything, from the fundamental particles to the first atomic nuclei, to the formation of galaxies and stars, and eventually to the planet we call home. Every single atom in your body, every particle of dust floating in the air, every spark of starlight you see in the night sky, all traces back to the moments right after the Big Bang. These moments were not just the beginning of our universe. They were the birth of everything. Now we're still far from the familiar universe we recognize today. The first stars, galaxies, and black holes are still many millions of years away. But we've witnessed the birth of the universe's ingredients, the seeds that would go on to create everything we see around us. In the next section, we will witness the culmination of this early phase, when the first true structures emerge from the cosmic soup. We have now reached the final moments of the first second of the universe, a second that contained more transformation, more violence, and more creation than any other moment in cosmic history. We've witnessed the birth of fundamental particles, the first atomic nuclei, and the foundations of the forces that govern our universe. But the journey is far from over. The universe is still expanding, still evolving, and the aftershocks of the Big Bang will continue to shape everything that follows. At this point, just a single second after the Big Bang, the universe is no longer the chaotic, incomprehensible inferno of its earliest moments. It has cooled from an unfathomable trillion degrees down to a still searing 10 billion degrees Celsius. Protons and neutrons have survived their battle with antimatter, and the first light atomic nuclei, hydrogen and helium, are floating in a sea of high-energy radiation. The four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, are now fully distinct, governing the interactions of everything that exists. And yet, there is still one crucial transformation left to unfold, the moment when light is finally set free. For hundreds of thousands of years after the first second, the universe remains in a state of intense plasma. High-energy photons, or particles of light, collide constantly with free electrons, bouncing around like water molecules trapped in a dense fog. This means the universe is opaque, completely impenetrable to light. There is no visibility, no transparency, only a searing, hot, glowing soup of energy and matter. But as the universe continues expanding, it also continues cooling. And then, at around 380,000 years after the Big Bang, the temperature finally drops to around 3,000 degrees Celsius, cool enough for electrons to combine with protons, forming the first neutral hydrogen atoms. This moment is known as recombination, a turning point that allows photons for the first time to travel freely without being constantly scattered by free electrons. Light is no longer trapped. It is released in every direction, flooding the universe with the first observable radiation. This is the birth of the cosmic microwave background, CMB, the very first light that we can still detect today. It is a faint glow, a whisper from the dawn of time, stretched by the expansion of the universe into microwaves. When we look at the CMB today, we are literally seeing a snapshot of the infant universe, frozen in time. But the story doesn't end here. The universe, now transparent, continues to evolve. The tiny fluctuations in density, created during cosmic inflation, start to form the first gravitational wells, pulling matter together in clumps that will one day become galaxies, stars, and planets. For millions of years, the universe remains a dark place, filled with neutral hydrogen and helium gas, but no light sources yet. This period is known as the Cosmic Dark Ages, a time before the first stars are born. Gravity slowly begins to work its magic, pulling clouds of hydrogen together, compressing them under immense pressure. And then, after 100 million years, the first stars ignite. These primordial stars, made entirely of hydrogen and helium, shine brighter and hotter than anything in the universe today. They illuminate the cosmos for the first time, ending the Dark Ages and beginning the era of reionization, where their intense radiation ionizes the surrounding hydrogen, allowing even more light to travel freely. The first galaxies soon follow. The first black holes form, and the grand cosmic structures that define our universe begin to take shape. The universe is no longer just a formless sea of matter and energy. It is becoming structured, filled with stars, galaxies, and the seeds of everything that will come after. And so in just 1 second, the universe went from absolute nothingness to a rapidly expanding, evolving cosmos, containing all the ingredients necessary for the formation of stars, galaxies, planets, and ultimately, life. Now think about this. Everything we see today, every star, every planet, every atom in your body, was forged from that single moment. The particles that make up your very existence were created in the first seconds of the universe's life. When you look up at the night sky, you are not just seeing distant stars, you are seeing the echoes of creation itself, and that is the incredible story of the first second of the universe, a moment of unimaginable energy, of cosmic violence, and creation of transformation that set the stage for everything that exists. But now the question is, what comes next? If we have unraveled the secrets of the first second, what about the future of the universe? Will it continue expanding forever? Will it one day collapse in on itself, reversing everything that happened in these first moments? Or is there a possibility that something even more mind-blowing awaits in the distant future? Let us know your thoughts in the comments. What do you think is the ultimate fate of the universe? And if you enjoyed this deep dive into the very first moments of time, don't forget to like, share, and comment to keep the conversation going. Your support helps us explore even more of these cosmic mysteries. Until next time, keep looking up, because the universe is always telling its story.